Hey guys, welcome to your lab over charge to mass ratio and of electron. You can tell by the title of this lab what the goal of this lab is going to be, and that's going to be, of course, to find what is the charge and mass ratio of an electron. So we're looking for Q over M, where Q is the charge and M is the mass of the electron. We're going to do this, we're going to be able to find this value by shooting a beam of electrons perpendicular to some external magnetic field. Okay, and now anytime we put a beam of electrons into an external magnetic field, we're going to have some magnetic force acting on those electrons, and this is given by the Lorentz force equation, which is this first line here. Okay, where Q is the charge, V is of course our velocity, and B is the magnetic field. Because our velocity and magnetic field are perpendicular to each other, we can just rewrite this equation, we can rewrite this cross product as just the scalar product of V and B. Okay, so now what we want to look at is how can we relate this Lorentz force to another known force, which we call the centripetal force. Okay, so let's see what is the direction of our force on this particular example that we have here. So we're going to use our right hand rule, and remember your right hand rule is your thumb is the force, and then we have V is our index finger, and B is going to be our middle finger. Okay, so our force is going to be V cross B. So we're going to put B out of the page. We're going to put, that means, so B is out of the page. There we go. B is out of the page because B is our middle finger. V is going to be our velocity. So we're going to rotate like so. And that means because our thumb is pointing down, that had this been a beam of positive charges, the force would act downwards. However, we know, or hopefully you remember from your electricity and magnetism courses, whenever you find the Lorentz force in this way, you're doing it for a test positive charge. So when you find it using the right hand rule, if your charge is negative, you just flip the direction of your force. So we said that the force for a positive charge would be downwards. That means because we have electrons which are negatively charged, the force is actually going to be upwards. So we have our force pulling up. So these electrons that are initially shot out to the right, because of this force, this centripetal force pulling inwards, they're going to curl around like so and return to their pot. So this would be ideally, if I could draw well, this would be a perfect circle here. Okay, and they're going in that counterclockwise direction. Okay, so the centripetal force is the same thing as the Lorentz force. The Lorentz force is what's making these electrons bend into this circular path. So we can set these two forces equal to each other. So let's go ahead and do that. So we have QVB is equal to mv squared over r. And I told you what we want to figure out in this lab is the charge to mass ratio. So we want Q over M. So let's rearrange this until we get there. So if we do that, you can do the algebra yourself. If you rearrange this equation, what you'll get is Q over M is going to be equal to, we have V, the velocity V, over BR, right? Because these cancel out. All right, so we need to know what is the velocity that this is leaving with, and we need to know what is the magnetic field strength. So before we can find those two things, we also need to know what is the radius of curvature of this circle that our electrons are traveling in. So those are the three things that we need to know. In order to find velocity, we need to understand something about how this beam of electrons is being produced. Okay, we produce these electrons, or we fire these electrons through what's called an electron gun. And what we do is we take a filament, and a filament is just a resistor which whenever we apply current will heat up and supply heat to the cathode, which is going to be our source of an electron. So this is just a piece of metal, okay, that we are going to apply a negative bias to, and this is what we call the cathode. And then this filament is going to heat up this cathode, which is going to liberate the electrons from the surface of the cathode. right, so now we have free electrons because we've taken this cathode and we've heated up and released some electrons. Now we need to accelerate those electrons, and that's what is going to be. And to accelerate them into a stream, we're going to use what's called this anode. So an anode is a plate with a hole in the middle that we're going to apply a positive charge to. So whenever we heat up this cathode and liberate the electrons, they're then going to be accelerated through this opening by this positive charge that we've applied to our anode. Okay, so the energy that these electrons have is going to be proportional to the potential difference, or the voltage, between our cathode and our anode. Okay, so when we're trying to find the velocity, we can first say that the energy that these electrons have is going to be QV, which is our equation for electrical energy. So they're going to have some QV, which is going to be equal to the kinetic energy that we have, because we're going to be converting this electrical energy that we're getting via this potential difference, and then it's going to convert to kinetic energy as it leaves as it leaves the anode. Okay, and from this equation we can now determine velocity in terms of other things that we're trying to look for. So if we solve this now for velocity, we're left with v, lowercase v for velocity, is equal to, we get 2q, capital V, the potential difference, over m. All right. Let's go ahead and plug this value for velocity back into our equation for Q over M. So this was kind of an aside. So we can then take Q over M is going to be equal to our velocity, 2QV over M, times 1 over BR. All right. Now, you can see we have a Q over M on this side, and we have a Q over M on this side as well underneath this square root. So we need to do some more algebra in order to get QM by itself on one side and then everything else on the other. So if you do this algebra, what you'll end up getting is Q over M is equal to 2V over B squared R squared, which is the final equation that we're going to use in order to determine this charge to mass ratio, Q over M. Now you might be wondering, hey, you didn't say anything about the magnetic field. And you're right. So we can't measure this directly, but what we're going to do is use the known equation given to you in your manual for what's called a Helmholtz coil. And so a Helmholtz coil is what we're using in this lab in order to supply our external magnetic field. And what it basically is just a coil of wire, round. It's a really wide coil of wire that we wind multiple times. And anytime we run a current through any coil of water, anytime you run current through a coil of wire, it's going to produce a magnetic field. And if you then take that wire and you put it into a circle, it'll produce a uniform magnetic field at the center of that coil. And that magnetic field is going to be equal to the following. 8 mu naught, where mu naught is the permeability of free space. N is the number of coils for one of the Helmholtz coils that we're using. I is the current that you run through the coil. Capital R is the radius of our coils. And then the square root of 125. Now this equation is derived for you. So you can look that up, and you should look that up in your manual to figure out where this comes from. But I'm not going to derive it here as it would take too much time. Right? But you should look at that on your own and make sure you understand where this equation comes from and how it's derived. Okay, so all we need to know in order to determine the magnetic field supplied by our Helmholtz coils is going to be the number of turns, the current that we're running through it, and the radius of the coils, where the only dependent variable that we're changing, or the only independent variable that we're changing is going to be the current, right? The number of coils and the radius are going to stay constant. So to change the magnetic field, all we have to do is change the current running through our coils. Okay, so from this equation, from this boxed equation, the main one that we're looking at today, you can see that I can change my voltage and I can change my magnetic field, and in doing so, we can then calculate the charge to mass ratio, because changing our voltage and changing our magnetic field is going to change the radius of this electron beam. So in lab, you can change either one. You can change the voltage, this accelerating voltage, or you can change the current being run through our coils. And doing so, it's going to give you a different radius, right? And then you're going to measure that radius, and then from all those values, we're going to calculate the charge to mass ratio, and we'll do this many times. And in doing so, you're going to be able to build a graph with many different data points. And on this graph, on this right-hand side, we're going to graph the radius of our deflected beam. On the x-axis, we're going to graph the voltage over the magnetic field, the accelerating voltage over the magnetic field, okay? And in doing so, we'll get a line, a straight line. And the slope of this line is going to tell us something about our charge to mass ratio. So it's going to be a way of getting an average charge to mass ratio value. So let's look back at this equation and try to get r squared by itself, because that's our y. Okay, and if we do that, the equation you'll get is r squared is equal to 2m over q v over b squared. So we just took this equation for the charge to mass ratio and we just rearranged it in terms, or we made it into a linear form where r squared is our y, v over b squared is our x variable. All right, and now you can see that the slope m, so here our slope is going to be equal to 2m over q. So whenever we graph this, you're going to get a value that's going to be equal to 2m over q. So you can't just leave that as is, okay? You're going to need to take your slope and you're going to need to take the inverse of it, all right? So if we are going to get our slope, and I want q over m. So to get q over m, I need to take 1 over the slope, which is going to give me q over m, actually q over 2m, and then I need to multiply both sides to get rid of the 2. So this is going to be 2 over here. So whenever you get your slope, you need to take the inverse and then multiply by 2, and then that will give you this q over m that we need. Okay? All right, guys, so that's going to be it for the in theory part of this lab. What you'll see next is actually the demonstration. We'll go through the procedure. I'll show you how changing the accelerating voltage and changing the current will change this radius. And from that, we'll do varying voltages and varying currents, and to build up a data table that we can then use to graph this line and then find our experimental value for the charge and mass ratio. Okay, so we will see you in just a second. Okay, guys, here's the setup for the charge to mass ratio. So you can see here is our tube, which holds our electron gun, and it's going to have some gas. So whenever the electron gets shot through here, we're going to be able to visualize the electron beam, because those electrons are going to collide with the gas particles that are in here. It's going to accelerate those bound electrons within the gas to a higher energy state. Those bound electrons, or those excited electrons, are going to fall back down and emit a photon that we're going to be able to see. So you're not going to actually be seeing electrons, but you're going to be able to see that the path that the electrons take, but because these electrons are going to be exciting this gas that's within this tube here. Okay, and you can see here we have our two Helmholtz coils, which hold lengths of wire wrapping around that we are then going to supply a current to in order to supply a voltage. So let's go ahead and turn our accelerating voltage up, which is right here. This is again what's pulling the electrons away from the cathode and accelerating them into our tube. Okay, and we can hopefully see that there's a beam there. Go ahead and put our back on. This will make it easier to visualize as well. All right, we have our beam of electrons coming out of our gun here. Okay, and now what we're going to do is turn our current on through Helmholtz coils, and you can see that current then supplies a potential, or that current supplies a magnetic field or creates a magnetic field within the coils, and then it bends that beam of electrons into a circle. Let's go ahead and turn the lights off so you can see this a little better. Okay. Yeah, so, and you can see that by changing our accelerating voltage here, we can change the radius of that tube. So if we go down, the radius goes down. If our voltage goes up, the radius goes up. And we can do the same thing by changing the current, which in turn changes the magnetic field. So if I can change the magnetic field, if I raise my current up, you can see that it decreases that radius, and increasing or decreasing the current through the coils is going to make that radius go up. All right. So there is a ruler in the back here. Let's go ahead and turn the lights back on. Move this now. So there's this ruler back here with this mirror attached to it, and if you look into the mirror, that's how you would measure the radius of that beam of electrons at varying voltages and currents. So we just want to get a nice survey of different radiuses. We can do that by either changing the accelerating voltage, the current, or both. It doesn't matter which one we're changing. We just want a series of different radiuses, and then once we get enough data, you can then use that to find the charge to mass ratio in the way that we discussed in our intro. Okay, so that is going to do it for this demonstration. You can see how changing the voltage and the current affected the radius here. You go ahead and use the data located on Canvas to then complete your lab report, and we will see you next time.